Hey guys! So, what we got going on today is we're going to be talking about electron configurations and all of the things that you can figure out given an element's electron configuration. To give us a little cheat sheet, right here I have an extended periodic table. So, it's one where the inner transition metals that are normally represented below the rest of the elements are actually inserted into the periodic table. This will help us clearly see where the F block is. Okay. Which, again, those ones are the ones that are typically below the periodic table. The D block are typically referred to as the transition metals. The first two columns, that's our S block. And the last six columns are our P block. Okay. In addition to that information, we'll talk about which energy levels each of those are. Those are the rows on the periodic table. Hydrogen and helium are in the first energy level. Lithium, beryllium, and so on, 2, 3, 4, 5, 6, 7. Okay. Now, typically, if you're just reading across and you're in the S block, that'll be 2S. However, for the F block, okay, the F block actually fills in at a lower energy level. So when you're filling in the F block, it's always going to be N minus 2. Again, these values over here are your N values. For the D block, it goes down one energy level, okay, just because of how stable they are and how complicated they are. They will always be N minus 1. So let's do some examples here. First example we're going to look at is oxygen. Oxygen is right here in the P block, okay, and it is also in the second energy level, okay. So we always start at the top with those first electrons. Oxygen's electron configuration will be 1s2, 2s2, 1s2, 2s2, and then we get in the P block and we go 1, 2, 3, 4. So 2p4. Okay? And that's how we read the periodic table to get electron configurations. Let's try a slightly harder one. Okay? We're going to try Mercury. Mercury is symbol Hg on the periodic table, and it's right here at the end of the D block. Now, when writing electron configurations for the bigger elements, we typically use the condensed or noble gas electron configuration. So you're going to look at Mercury, you're going to go up one row, and look at the noble gas that comes before Mercury. In this case, xenon. We write its symbol in parentheses. What that tells us is that Mercury's electrons look just like xenon's, and they have some extra ones added on. So after xenon, we get down to the row 6, the row where Mercury is. So it's xenon, 6s2, and then we get into the F block, okay? The F block always goes down 2 energy levels. So after filling up the 6x, it actually goes back down and fills up the 4f. 4f, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 4f, 14. Okay? Then it'll go and fill up the 5d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? Got it? Okay, cool. Let's try a really long one. And then we're going to use these to answer some questions about them. Okay? Let's look at the electron configuration for americium. Okay? There's americium down there in the bottom of the F block. Okay? Americium, same, we're going to do its noble gas, so we go to the noble gas that comes before it, which is radon. So it looks just like radon. plus it has 7s2, 5d, 1, 2, 3, 4, 5, 6, 7. 5, oh, I'm so sorry. That is my bad, not 5d, 5f, 7. Okay, so we're going to look a little deeper at each of these electron configurations and see if we can use them to determine other things about the elements. Okay, let's first look at oxygen. Okay, there's oxygen's electron configuration written out again. Let's go ahead and use that to do the Bohr model. Bohr models are simplified models where you represent the nucleus as a dot, and then you have the electron energy levels around it. So in the first energy level, oxygen has 2 valence electrons. 1, 2. I'm using green dots for the electrons. In the second energy level, oxygen has 2 plus 4, or 6 electrons. 1, 2, 3, 4, 5, 6. Okay. For right now, I'm just putting them wherever because it doesn't really matter when doing a Bohr model. Okay. Let's go ahead and do the orbital diagram for the Bohr model. That one goes in a little bit more detail because it shows you not only which energy level it's in, which orbital it's in, S or P, but also which specific suborbital within there, and the spin of the electron. So they're very useful for helping us figure out things like unpaired electrons and quantum numbers. Okay, so for oxygen, oxygen has a 1s orbital, okay, and it has 2 electrons in it. In orbital diagrams, electrons are represented as arrows, so an up arrow and a down arrow. It also has a 2s orbital with 2 electrons in it. And then it has a p orbital. P orbitals have 3 suborbitals, so we want the p to have 3 blocks in it. Now, when filling in the electrons, we have to fill them in 1 in each orbital before we double them up. This is called Hund's rule. Basically, you want to minimize electron-electron repulsions, so you want to spread out the electrons, and that's what atoms do. So we put 1, 2, 3. Now there's nowhere less for that 4th to go. It can't go in its own orbital, so it will fill up the second one in the p. Okay, and we can use this to answer questions about oxygen, like how many unpaired electrons does oxygen have? Well, it has this one and that one. So it has 2 unpaired electrons, which means it is magnetic. When something has unpaired electrons, we say it is paramagnetic, meaning it will react, in a magnetic field. Okay? Call it paramagnetic. Okay. Now I wanted to go over a little bit about quantum numbers. On the AP chemistry test, you don't have to be able to assign quantum numbers, but you should be able to recognize them. Okay. So let me clear up and make some room here. N, L, M sub L, and M sub S. N, that's the principal quantum number, aka the energy level. L is the sp, d, or f, which orbital it's in. M sub L is which specific orbital it's in, so it can range from negative L to 0 to positive L. And then M sub S is the spin, whether it's an up or a down. The values for that are always going to be plus or minus 1/2. Okay, so I'm actually going to go through and assign quantum numbers to every electron in oxygen for you. Okay, so let's start with the 1s electrons. We have 2 1s electrons. They're both in the first energy level, so N is 1. And my smart board is being dumb. is which orbital. S has a value of 0. So 0. Since S is 0, since it's in the S orbital, L is 0, M sub L can only be 0. And one of them is going to have a value of plus 1/2, while the other one, which is almost exactly the same, still a 1, 0, 0, it's going to have the opposite spin, minus 1/2. The Pauli exclusion principle says that no two electrons can ever have the same exact quantum numbers. Okay? What about the two in the second energy level? I'll use red for those. They're in the second energy level, so their principal quantum number is 2. It's an s orbital, so that means an L value of 0, which means an M sub L value of 0. And we have the plus 1/2, and then the exact same set of quantum numbers, but with the opposite spin, with the down arrow instead of the up arrow. Okay. Now let's look at the P ones, because that's where it gets a little bit complicated. Okay. I'm going to go back to blue for the P ones. We have 4 of them. So first I'm going to talk about these two. Okay. Those two, they're in the second energy level, so their principal quantum number is 2. Okay. L for a p orbital is 1. Okay. Now M sub L can have values from negative L to L. So what you can kind of picture is in your orbital diagram, you can do that. Negative L, so negative 1, 0, and 1. Those are going to be my M sub L values for the different p orbitals. Okay. So negative 1, 1, it's in the first one, so I'm going to call that negative 1, and it's an up arrow, so plus 1/2. Then the second electron in that orbital has the same values, but with minus 1/2. 2, 1, negative 1, minus 1/2. Okay, so that's for these 2 electrons. Okay, now this electron, okay, is in the second energy level, so it has 2. L, it's still P, so it's 1, but now its M sub L is different because it's in a different orbital. So that one is 0, and it's an up arrow, so plus 1/2. This one right here has almost the same, but with a different N sub L. It's in a different orbital within the P. 2, 1, 1, plus 1/2. Okay. So those are all the quantum numbers for all 8 electrons in oxygen. Okay? Let's go a little bit deeper into oxygen and talk about PES. What PES is it measures the difference in the energies of the electrons based on their ionization energies. So how it normally works is you have the ionization energy on the x-axis, but the difference is that the big values are on the left side, where the small values are on the right side. So it goes from low to high. Okay? And then on the y values, you have your relative number of electrons. Okay? So for oxygen, I know the highest number is going to be 4, so I'm just going to do it like that. Its 1s electrons are going to be the highest energy, so we're going to see a peak there. Okay? And then there's going to be a big jump between that first energy level and the second energy level. Then you're going to have your 2s electrons. Your 2p has twice as many electrons in it, so it's going to be twice as high a peak. Okay? So there's the 1s, the 2s, and the 2p peaks of the electrons. Okay? That's a general idea of what the PES, or photon-electron spectrograph, would look like for oxygen. Okay. Let's look at those other electron configurations we wrote down. We wrote down the one for Mercury. Okay. Mercury looks like xenon with the 6s2 and the 5d10. Its orbital diagram, we can do a condensed one with the xe, that 6s orbital, and then d orbitals have 5 suborbitals in them, okay? So it has 1, 2, 3, 4, 5. That will be my 5D block. And in xenon, all of these are completely filled, 2 and 10. So 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? That's what an orbital diagram would look like. Now Mercury forms a 2+ ion. Okay? It will become Hg2+. Why? Okay? The reason has to do, of course, with its electron configuration. When something becomes an ion, it always loses its outermost electrons first. And though the 5D are filled second, the 6s is its outermost electrons, okay? It's going to lose its 2 6s electrons. So, its electron configuration for the ion is going to look like this. It's just like xenon. It no longer has those 6s electrons, so it's just xenon plus the 5d10 electrons. Okay, so that's how those can help you figure out what ion those transition metals form, even though it's not necessarily an easy thing to know. Okay, let's look at one more example. We're going to look at americium. Okay, americium has the electron configuration of radon. It has a 7s orbital, okay, with 2 electrons in it. And then it's in the F block. F block elements have 7 orbitals in them. Okay, 7 orbitals in the F subshell. So 1, 2, 3, 4, 5, 6, 7. Okay, so that's my 5F. I'm going to go ahead and fill in my electrons. 1, 2, 3, 4, 5, 6, 7. Okay, americium is a particularly stable element because of that half-filled orbital. Okay, it likes that. It minimizes the electron-electron repulsions and makes it very happy. Let's talk about the nuclear charge. What is the nuclear charge on those 7s electrons? In order to understand that, we first have to know the nuclear charge of americium. So the nuclear charge of an americium is 95. It's number 95 on the periodic table. So it has 95 protons in its nucleus. Okay. Now, all of those are inner electrons except for the 7s ones. So its total amount of inner electrons is going to be 93. Okay, because even those 5F, which got filled after, still went inside of those 7s electrons. So they contribute to the shielding of those outer electrons from the inner one. Therefore, the effective nuclear charge on those 7s electrons in the americium atom is going to be 95 minus 93, or 2. Okay? Those 7 valence electrons only experience a +2 charge, pulling them in. Okay? So that's a little deeper into orbital diagrams and electron configurations. Okay, cool? Okay, cool.